Today we're talking about prediction of mechanical responses for additively manufactured lattice structures. Students involved are Sydney Cruz-Rodriguez, Connor Rebodos, and Devon Stapleton. Our faculty advisors are Dr. Chen Kan and Dr. Xin Liu. Our graduate student advisor is Zehao. Here's an overview of our poster and some of the components that we'll be covering today, which is our introduction, research framework, experiment setup, and our results. For our introduction, additive manufacturing has been widely applied in producing metamaterials due to its high complexity in building complex structures. Some of these complex structures are lattice structures. There is an urgent need to develop a data-driven approach for fast assessment of process-induced geometric imperfections. With that in consideration, our contribution into this project is a data representation method based on heat kernel signatures, also referred as HKS, to employ and decode geometric information. With that, a deep learning framework is proposed to model the relationship between metamaterials geometry and its mechanical property.
For our research flow, we begin with the additively manufactured lattice structure and their imperfections. After this, we have the structure, we take it and send it through the point cloud where the 3D scanners capture its geometric details. We then use a heat kernel profiler to produce an image representation of those thermal signatures. The output image representation goes through the CNN model to generate a predictive value for Young's modulus.
We take a deeper look into the heat kernel profile. There are 6 different components that go into the profile, which would be point cloud, mesh, Laplacian, eigensystems, heat kernel signatures, and the heat kernel profile itself. The heat kernel profile is a representation of individual mark points in the point cloud. The profile tracks its progression of thermal signatures over a specified period of time.
CNNs are comprised of convolutional layers, max pooling layers, and hidden layers. They are able to take an input and then use these layers to produce class scores for classification purposes. In the convolutional layer, this is where the majority of the computation happens, which requires an input, a filter, in this case a heat kernel profile, and a feature map. In our experimental setup, we analyze the mechanical properties of 300 unit cells of auxtic structure. 300 heat kernel profiles corresponding to 300 auxtic unit cells are generated, using the images as inputs. The Young's modulus of each auxtic unit cell is used as an output data and computed through finite element method. The goal of the ablation study is to evaluate the effectiveness of the proposed framework while several of the parameters are tuned. We use k-nearest neighbors and Raymer force regression models as regression methods to compare with our proposed framework.
With our experimental results, we were really mainly focused on capturing 3 indicators of regression performance. Those indicators were R squared, the variation correlation, which is found in our model, as well as 2 measures of accuracy, which are the mean absolute percentage error and root mean squared deviation. As we take a look at the ablation study, we note that in Table 1 and Table 2, it depicts a tuning of 2 parameters, learning rate and epochs per batch. Note that the learning rate controls how significantly the model responds to error, while epochs determine how many times each image goes through our network. Within the model, we see that our CNN model is robust in responding to different values for epochs, but is sensitive to the learning rate. When taking a look at the benchmark comparison study, our CNN model outperformed our other 2 benchmark regression models, random forest and k-nearest neighbors. As you can see, in all 3 of the major categories that we captured, our CNN model outperformed both models.
Overall, we want to say thank you and a big thank you to the College of Engineering Research Experience for Undergraduates REU program and the University of Texas Systems STAR program for supporting this research.